Hello everyone. This is the video for Chapter 3 for Astronomy. I know it's a little late because this your required homework is due this week on week 4, and it's kind of we've stretched this over 2 weeks because it's a big topic, and I'm not going to spend a huge amount of time on this. I'm going to tell you interesting stuff and hit the high points, hit the things I think are important for you to know. But mostly you're doing a lot of the stuff. You're researching a lot more of the topics that are coming up here. So I do want to make sure that after this video, I do a couple calculations in another video for you. Just to make sure that everything's, the calculations in this chapter are pretty straightforward, I think. And then next week is the one where they get kind of out there. So we'll see how it goes. All right. So the whole point of this is, why do we even do astronomy in the first place? All right. I mean, we kind of understand it, at least from the modern perspective, is we kind of want to know what's out there, and we have some ability to send stuff out there, and so we want to, deal with that. But from the ancient perspective, they're still wanting to know what's out there, and they're wanting to have useful tools for their life. Right? I mean, that's what we're doing. We put satellites in space, and then suddenly we have TV and internet and GPS and all sorts of surveillance and imaging. And then we can put telescopes in space and see out, the rest of the universe. But they're looking, the ancient civilizations are more trying to, they're trying to start agriculture. They're trying to basically start civilization. And a lot of what we take for granted is stuff that was invented back then through astronomy. Right? It's the idea that we can keep time with some measure of accuracy, that we can keep track of the seasons and the calendars, that we can do a lot of astronomical prediction, is built on work that's thousands of years old. So some of the very earliest uses of the sky is to predict seasons. In particular, looking at rainy versus dry seasons. If you look at the moon is going to orbit in a cyclical way such that, right, remember, it's tilted at a little bit of an angle. Its orbit is compared to the Earth's, right? It's something like 5 degrees off the Earth's orbit. So as it orbits around, our perspective of it changes. And what they did was they looked at the crescent moons and looked at the rough angles and noticed that it was in a cycle. And so they could match up those cycles and use that to predict their dry and rainy seasons. Timekeeping. The reason we've got 7 days in a week is particularly because they're linked to 7 objects in the sky: the sun and the 6 planets, and the moon. A sun, moon, 5 planets. There we go. And so, in particular, English takes names from Germanic and Norse, and in French and Spanish take it from Greek and Roman. So there's more time telling. There's using shadows to tell the time of day. Also in Egypt, they used the appearances of stars to tell seasons. Basically, lots of timekeeping built up, and eventually you got proto-observatories, like Stonehenge is here, which oddly is not a hinge. A hinge is defined as kind of the opposite thing of Stonehenge. But there's lots of things like Stonehenge that are littered through, remains of people's work, which, here are sort of the hinges of Great Britain. And what they're trying to do for a lot of these is have places where astronomy can be made use of to keep time, keep calendar. All right, this is Stonehenge. And eventually we look at the alignments and we realize that the structures that are built are aligned for the solstices and for the moon rises and moon sets. So this is ultimately a way of keeping a calendar, is that you do observations and you know when the sun rises over this particular alignment, you get, that's your summer solstice. So there's other versions of this. In Central America, there are lots of structures, lots of pyramids that are effectively, there's lots of sites, and they're effectively ways of getting above the forest canopy to do astronomy. So we can see different perspectives. There's lots of these structures that are effectively ways of getting to where you can see something and do your astronomical observations. Now, a lot of this is being done also in a religious sense. Is the people who can do astronomy are going to be the people with resources, which tends to be your clergy and your government. And so, in a lot of cultures, those are kind of intermingled. And the people who can do astronomy, who have the funds to do it, who have the resources to build these structures, they're the ones doing it. And so you see evidence of the religious aspect as well as the astronomical aspect. So, and then there's simpler structures. Not everything's a great big pyramid. This is a turret. And the idea is that it's basically a round house with holes in it, and the holes allow you to see events as an observer at the center. And so, you can find particular stars rising or setting and, use the particular alignments to do your observations. And so there's other versions of this. This even goes, this is basically a structure for people to live in that also has astronomical alignment. And there's a few others. Sometimes it's just as simple as a hole in a set of rock that marks, when the light shows up in the shadow at a certain spot, that's the particular, in this case, the summer solstice. And there's lots and lots of these ancient structures which correspond to different purposes. People are observing different things. Here, the moon rises on cycle. We talked about the metonic cycle that governs when eclipses occur, and the cycle of the lunar months. Yeah, that's the one I'm looking at. The cycle of the lunar orbits. And so this is, trying to measure particular events out over a couple of decades. And there's a few others that we're not certain of as to exactly what they're doing. In Peru, there's this network of patterns called the Nazca lines. And they make these patterns that look kind of like birds. And, you can imagine a hummingbird. This is the beak and the head, tail, and wings. And some of these patterns line up with stars. Um, there's some other ones. Machu Picchu has structures aligned with the solstices. Um, and then there's some that just, they don't leave remnants, but they're still, in a sense, being practiced today. Is in the South Pacific, one of the techniques for going island to island is using celestial navigation. And so they build maps out of materials they have available that are essentially star charts. They also had the ability to read the waves and how they broke against land. And so they'd have similar charts for waves crashing against the patterns you would see away from land tell you how the waves are interacting with the land. And so, there's a lot of, this kind of gets into the reason astronomy was so big 500-600 years ago is because of navigation. It's a tool that sailors could use to guide their boats across water without landmarks. There's some even earlier evidence. Right? There's some famous cave paintings in France, and the interesting bit is the sort of, let's see if I can get a laser pointer in here. Yeah, these little bits of what look like smudge seem to be evidence. Maybe they're lunar phases. Like, it's not, you would think it's kind of hard to miss lunar phases, but people took the time to actually draw them out and show that maybe they repeat. Of course, they've also drawn a horse here, so it's kind of up to interpretation a bit. All right, so there's a lot of stuff that is fairly kind of I'm trying to do here. Right, there's a lot of purpose to this stuff, but it's really kind of a little hard to figure out some of what's going on because there was no records. This is going to be an important theme through the chapter, writing the stuff down and preserving it. Right, publishing your work makes it useful. And so before there was writing, there wasn't a whole lot of reliable, repeatable astronomy. There was a lot of memorization, a lot of recitation. You would hand it down by word of mouth, and it really took to the development of writing and the development of record keeping. Right? The idea that you could carve something on stone or clay or write it on paper and keep those records. And so, we're talking about 18,000-year-old observations on a cave wall, but really the useful bits is where someone wrote down what they did, and that stuff's about 4,500 years old. And a lot of these things that we're talking about is a lot of speculation, a lot of figuring out from circumstance what's going on. Now, why can I not? Let's go. Here's some records. Basically, the Chinese astronomers were the kings of noting new stars in the sky, and in particular, noting supernovas. They have records of these events occurring that we can correlate to the actual remnants that are in the sky. Right. And so there's some other one. Here is a recording of the actual discovery that this was writing that we could translate and figure out what it is kind of an interesting tale on its own. I'm sure you can find some information out there about this. I'm not an expert at all, but this is supposedly astronomical observations that have been recorded on a clay tablet, and then they were preserved by baking it so it's, you know, more rock-like. And then here's kind of drawn out sketches of those things. Again, more clay tablet astronomical records. Other recordings, basically places where records had to be kept. That's a good way of keeping astronomical records. In particular, in Central America, there were lots of recordings in a sense of calendar keeping. Right? This is what's called the Dresden Codex. And it's basically a set of records that are keeping account of observations. In this case, some of them are eclipses, some of them are appearances of Venus in the sky. The idea is it ended up being a calendar. So there's Venus. And so you might say, well, when does it appear in the sky? That depends on where you are in the Earth's orbit, where Venus is in its orbit. So a lot of this record keeping, and we'll come back to this because the buildup of this is that there's a calendar, and the big baloney science bit is when that calendar ends, that's the end of the universe. But we have calendars, and they have an end, and the universe doesn't end. Well, maybe it did in 2019, but probably the universe doesn't end when we buy a new calendar. So all of this astronomy is well and good. It's record keeping, it's tools for particular purposes. It's for timekeeping, it's for knowing when to plant crops, when to have events in society. And there's other purposes for it too. But none of it is really trying to figure out why. Why are stars fixed in the sky? Why are the planets moving around? Why do we see things in astronomy? And some of the first people who recorded that they considered why were the ancient Greeks. And the idea is that they made models of nature. What's pictured here is essentially a geocentric model. The idea is the Earth's at the center of the motion, and we see things moving around on essentially spheres. They're kind of funny-looking spheres. The idea is that you can map out the different positions as a small model that you might even be able to build and carry around. So the point is that they made models, and the idea was the models were attempting to understand nature, but not put in a supernatural explanation. They have to be just as explainable as anything on Earth. So a common example I have is in the mythology of the ancient Greeks, Apollo is a chariot driver. He drives a chariot that's on fire and drives it across the sky and then parks it at night and brings it back and drives it the next day. And that's the sun. Now, that's a well and good story, but it doesn't explain it. Right? It's a supernatural cause. It explains that the sun goes by. It's saying, well, effectively it's part of this great big story. But it doesn't, it isn't a natural explanation. So the idea was they wanted to be able to make measurements. They wanted to be able to quantify their ideals and do useful math and have their ideas fit the observations. And if you get a wrong prediction out of your model, then you can update it. That was kind of these models build on what other people have done, and they fix problems with it. Right. So coming from this, they gained a fair amount of information. Um, they knew the shape and the size of the Earth and the Moon. They understood why there were phases. They understood why there were eclipses. They could measure the precession of the Earth. They realized that the sun was a much larger object than the moon that was far away. They built these models, and the models developed from less good to more good. Right? Is that one of the famous models of the Earth is that it's flat. Another famous model is that it's round in some sense, right? Because if you go north to south, you see different stars, but if you go east to west, you don't. Right? If you move by latitude, you see a different sky. And so something that is obviously curved in latitude but not in longitude is a cylinder. But people thought the Earth might be cylindrical. Eventually, they realized that it's spherical makes more sense, and they were able to measure the shape and the size of the Earth. And so there's a lot of development in this astronomy that guides their models. All right, so here's an outline. There's a lot of, I recommend you go look um, at these slides. There's the realization that the Earth's a sphere, a realization of the structure of the Earth and the heavens, and how time, how periodic motions occur. There's also some other stuff going on. Up here, Plato and Aristotle are going to argue for sort of a perfection in the universe, and perfect circles, perfect spheres, an Earth-centered universe. And there's going to be other people who are talking about, well, the Earth rotates, and possibly the Earth goes around the sun instead. And there's lots of stuff going on, but the people up here in the top layer of this are the ones that are developing the geocentric model. The idea that there is a natural explanation for the motions of things in the sky, and those explanations can be explained. Those explanations include that the Earth is the center of the universe. So there's a lot of stuff going on. Chemistry is going to end up starting here, that stuff is built from atoms. Um, Aristotle might be the one guy that got it the most wrong in all the fields that he considered. There's some famous thoughts of philosophers of his time talking about a man is a featherless biped, and another philosopher would pluck a chicken and show it to him and says, "Behold your man." So you can go look up Diogenes if you want to hear about that. Aristotle did a lot of thinking, but he was guided a lot by perfection in the Platonic ideal, which oddly enough was created by Plato. And he kind of explained a lot of stuff, and his explanations, it was obvious he didn't do experiments. And once you do the experiments, you realize that things aren't the way he described it. But there's a lot of other stuff that's right and is dealing with, measurement in some sense. So, eventually, we come up on the people who figured out sort of key things in modern astronomy. Like the idea that stars are of different brightnesses and you can categorize them. That comes from Hipparchus. He also discovered precession and came up with some of the ideas of fixing the geocentric model so that it made better agreement with what was observed. And eventually Ptolemy finalizes the model in a sense, is comes up with something that will last for 1,500 years. So there's a lot of geocentrism, um, but there's also some heliocentrism. Um, Basically predicts the sun's very far away, and he's okay with the idea that we can't see the stars move because they're very, very far away. That there's no stellar parallax just because the universe is too big. But a lot of people weren't happy with that too big idea. They wanted a smaller universe. And that means that the Earth has to be not moving. It has to be at the center of it. And so, there's an outline of who did what. There's the idea that Earth might be cylindrical because of how the constellations appear. Then the idea, no, everything's this perfect sphere, perfect shapes. People measured the circumference of the Earth. We'll talk about that in a second. But in particular, the idea that, well, if our observations don't fit the measurements, well, let's try more spheres. Let's try to fix everything. And Aristotle, again, thinks, hey, maybe these are actual spheres. Maybe there's a clockwork to everything. So a lot of stuff is done to fix up geocentrism, but and there's a reason for it. There's one is that it explains the two big things going on, right? Explains that you can't see the stars move due to parallax. And then you also have to explain why you can see the planets move and they move backwards at times. So you have to explain that, and that structure they're willing to accept. They figure it's probably easier than other explanations. And that's kind of the big thing. Stellar parallax, it drives the geocentric idea. Right? We should be able to see if the Earth is moving, the motion of nearby stars, but we don't. And we think they're a lot closer than they appear to be. Right? We don't. They don't want to accept that stars are very, very far away. So they figure that the Earth doesn't orbit. It has to be the center of the universe. And so they come up, after some other stuff. This is where we're going to talk about the measurement of the Earth's circumference. And basically the idea is it's measuring shadows. In one place, they could observe that the sun was directly overhead on a particular day. Or in particular, they looked in a well and they saw the reflection of the sun in the well, and they knew the sun was directly overhead. And then a certain distance away, they could measure the length of the shadow and tell that the sun was about 7 degrees off. And this is 7 degrees over effectively 5,000 miles. It's not quite, actually it's not 5,000 because the Greek, like the Romans had a measure of the mile that was about a mile. The Greeks had it and it was about a sixth of a mile or a sixth of a kilometer. So doing this measurement, it's just fairly simple geometry. Is the arc length between the two measurements represents 7 over 360 of the circumference of the Earth. And they calculate it out. It's about 42,000 kilometers. And that's relatively good. This should be about 40,000 kilometers around. But it's a good enough measurement. So they're using their evidence to figure out what's going on. But the underpinnings of the model is kind of the idea that the heavens are better than the earth. They need to be perfect. Perfect spheres and perfect circles for everything to move on. And that makes retrograde motion hard to understand. The idea is that if something's just moving at a constant velocity on a circular orbit, how is it that it's going backwards at times? Right? And it makes sense from the Earth moving, because the Earth could just lap another object. But it doesn't make sense if the Earth's not moving. So there's lots of observable retrograde motion. These are all of Mars, I believe. But you can see the motion occur taking the picture at the same time every night. You see, a lot of these patterns. And so if you're looking at this and if you're looking at the animated picture here in the lower right, you're looking at it and you're thinking, I'm not moving. That is an object that's kind of rolling around the circumference of something. All right, they're attacking more spheres onto their model to make this work. And so that gets us to the Ptolemaic model. And the idea is that he combines a bunch of explanations and a bunch of fixes to eventually get a model that is predictive, and it is accurate enough to navigate by, and people use it for 1,500 years. And the gist of it is that there actually are these other circles that the planets move on. Is that the planet moves on a small circle, and the center of the small circle moves on the big circle. And, of course, they have different names. These circles are called epicycles, and they don't quite orbit with the Earth at the center of the orbit. The Earth is a little bit off, and they orbit some point off of the Earth. All right, so there's a bit of wobble that comes into this, and that kind of basically adding and shifting circles around allows it to fit the observations that they actually see. Now, this sounds kind of like, well, isn't it just simpler to not do this? All right, but they're seeing what, they're taking the failure to observe something and they're translating it as, well, there is no stellar parallax. The Earth's not moving. And then using that, they're just making bigger and bigger and bigger additions that make smaller and smaller and smaller fixes to the model. And so, it becomes good enough to make predictive motion, because if you pretended that the Earth was stationary, then the motions of everything around the Earth are going to be a little bit unusual, and you do have to tack on stuff like this. Like, the model isn't a description of the universe, right? We know that's wrong, but it is a mathematical model in the sense that you can make predictions with it. And if you fix it up enough, it still works. So this is the gist, is the motion of the planets go, and sometimes they actually do go backwards, because they're moving on a small circle, and the small circle moves on the big circle. That's the gist of it. And the big thing about this is Ptolemy published his work in something called the Almagest, the greatest compilation. There's an Arabic translation that survives of his model, and basically he published his research, and it was shared widely, and it went to several civilizations, and in particular the Muslim world kept libraries, kept records, and kept doing astronomical observation, kept testing the model, kept using it for navigation, and continued to spread it. And so the model worked, and it worked for up to 1,500 years, and it worked good enough that people kept using it. That's kind of, just because it didn't describe the solar system doesn't mean that it wasn't useful. So eventually, it does come up with errors. It does become less useful. And so people are basically the whole renaissance of astronomy is trying to fix the model because it's no longer as predictive as it once was. So people are working on this problem, and Copernicus, he comes up with an idea of let's abandon the geocentric model. Let's go with a heliocentric model. The sun's at the center of the universe. Now, he also wanted to make as little changes as possible, so he kept the perfect circles. And his model wasn't any better. And so there was no reason to switch from it. You couldn't get better predictions, you couldn't navigate better with it. But that it did start the idea that we should consider other models. Now, Copernicus, kind of interesting. He was a fairly well-off person. Raised up good schools, very good at math, very good at astronomy. Came up with these models. There's not a huge amount going on because, the big thing he's known for is proposing that we can try a different model. So people start looking, thinking maybe better data will tell us something, and we come up on Tycho Brahe, who's known as Tycho instead of Mr. Brahe, he's so I'm going to talk to you completely aside from the notes here. This is just anecdotes because this guy is kind of out there. So aside from the notes, he basically invented graduate level research. He had the idea of building a facility for research, like building an observatory, staffing it, and having people to help out with the measurements. Now, aside from that, he had lived a very colorful life. This painting of him is not realistic because at this point in his life, he didn't have a nose. He lost it in a duel. Duels in that time were fought with swords, and the duel was over a mathematical theorem a mathematical hypothesis that a conjecture. Tycho took one side, his opponent took the other. They weren't good enough mathematicians to solve it, so they fought over it. And he lost his nose in a battle, in a duel. And so he had a fake nose. He'd have gold noses and brass noses. He had a formal one and a work one. So he also kept a pet elk, or is it a moose? I think it's a moose. He kept a pet large deer-like animal. I think it's a moose. And the moose died because it fell down the steps because it got drunk at one of his parties. That was the other thing he was known for, is he would seek funding. And one of the ways he would seek funding is by attending and going to very large parties and getting well and truly wasted. He got his moose drunk and it fell down the steps and died. When he actually did work, as opposed to basically administrating work, he is basically the best naked eye observer ever. Mostly because of his tools. He built an observatory that was basically a giant protractor, and so he could measure down to 1 arc minute the positions of stars, basically by looking through a tiny pinhole in a wall while his assistants moved him around on chairs. So he still couldn't detect parallax, even with being the best observer of his time. So he thought the Earth had to be at the center of the solar system. But he decided that maybe the other planets go around the sun instead. Maybe he could make a hybrid model. And that didn't work. That didn't work at all. Like, that was a horrible model. But he had the sense of, he had this idea of hiring help and getting them to work on the problem. And he hired Kepler, which we'll talk about in a minute. And his idea, Tycho's idea, was he'll get Kepler to explain one orbit, and Tycho will generalize it and basically be the first author on the paper and get all the fame for it. Right. So he's a very good observer, and that's kind of the key contribution he had. Is his observations are the ones that allow for the actual model to be developed. Now, Tycho eventually, it's rumored that he was poisoned, and certainly there was a fight over his data after he died. But the apparent story, the one that's commonly told, is he goes to a party seeking funding, essentially. He goes to a party where the king is there. And the protocol for interacting with the royalty at the time was you do what they do. And you don't get up before the king gets up. And so Tycho drinks a lot and doesn't go to the bathroom. And it's said that his bladder burst and he got an infection and died. Now, we're not sure if that's actually what happened or if he was poisoned or, there's a number of theories. But certainly he died of some sort of sickness that came shortly after these events. But anyway, he hires Kepler. Kepler is kind of an odd duck. He's always poor. Doesn't get to go to the best schools all the time, but he gets to be a fairly good mathematician, fairly good astronomer. And a lot of his fundraising is astrology, oddly enough. And we'll talk about that in a little bit. So Kepler's looking at Tycho's data, and he's trying to fit it to circular orbits. And he realizes that if Tycho can measure down to 1 arc minute, and he can't fit the model to any better than 8 arc minutes, it's probably not a circle. And so he says, well, what if we take a mathematical object like a circle and we make it slightly less perfect? What if we go with ellipses? And that's it. That's the solution. He says, let's throw out the circles. And so we can describe the model here. So an ellipse is not just an oval draw normally, but an ellipse is mathematically distinct from just a normal oval shape. So I want a pointer here. So a circle, you can imagine you draw it with a string and a nail, and the string has one length, and so the circle has one radius all the way around. So if you've ever done this in elementary school, you draw you pick 2 nails, 2 centers of the ellipse, the focuses, or the foci, and use a string looped around them to draw a shape. And the idea is that the distance from one focus to your pin to the other focus is a constant, no matter what. And you can see that if you have the formula for a circle, it's x squared plus y squared equals the radius squared. Here, there's coefficients to those x's and y's, and that's what sets up this sort of squashed shape. And the further apart you move the focuses, the more squashed the ellipse looks. For most of the orbits of the planets, they're fairly close to circular. The ellipse is just a small correction to a circular orbit. but you need to have that small correction to make everything work. For other things like comets, you have very eccentric orbits. So Kepler come up with 3 laws. One is that every orbit is an ellipse, and the sun is at one focus of the ellipse. All right, so this is a very drastically stretched out ellipse, but it kind of labels out the key features. Is that the distance, half of the longest distance, the thing we'd normally call the radius, is what's called the semi-major axis. And then the closest point to the sun is what we call perihelion, and the furthest away point is the aphelion. So, first law, ellipse, sun is at the focus. The second law, he says, is making a note of the speeds of the planets as they go. So what he noted was that planets that are very near the sun are moving fast, and then when they get far away from the sun, they slow down a bit. And so on this drastic image, you can kind of compare the time it takes to move from one of the shaded area edges to the other is the same on both of them. Right, that is, in equal measures of time, the planet doesn't travel equal distances, but it sweeps out equal areas. It's either a long, thin triangle or a short, fat triangle. And this explanation, from Kepler's point of view, is a way of explaining that the planet moves faster when it's closer to the sun and slower when it's further away. Now, in Chapter 4, we will talk about this, and if you're in physics, this will be Chapter 12 in the physics text. We'll talk about that this is a matter of conserving energy, is that there's energy due to the thing moving and energy due to where it is, and they're moving backwards and forwards. And this is also conserving momentum. The idea is these things have to have a certain amount of momentum that's conserved, and that momentum's a product of the distance and the speed. So distance gets small, speed gets big. So, but the way he expressed it was this idea of sweeping out an area. It sweeps out equal areas in equal time. All right, so the third law is comparing different planets. And so at this time, they didn't know the size of the solar system. They didn't know the distance from the Earth to the sun. But they could measure relative measurements. And so he comes up with this idea that the further away you are from the sun, the slower on average your orbit is. And so you can come up with a relationship between the orbital period in years and the average distance in astronomical units. All right, and that's what he's doing, is setting up a ratio of the other planets to the Earth. Right, because the Earth will only go around in 1 year, so 1 squared is 1 cubed, 1 astronomical unit cubed. So he comes up with this p squared is a cubed relationship. Now, again, next chapter, Newton will expand on this, so it applies everywhere in the universe. But if you plotted this out, you plotted the period versus the distance from the sun, you would get this weird curve. But if you plot the period squared versus the distance cubed, you get a straight line. And so the early the close-in planets all fit in a very small cluster of spots, and then Jupiter and Saturn go out. And that's the solar system as they have seen it so far. And the correlation to that is if you plot the orbital speed versus distance, you realize that the further away it is, the slower it orbits. So that's all well and good. Kepler's got the theory. It seems to work. It seems simpler, but there's some objections. All right, and in particular, these objections are coming, one, from the church, and two, from people who are still holding Aristotle up as a big deal in philosophy. And some of Aristotle's arguments are here, and some of, you know, essentially the objections are, right, if the Earth is moving, stuff that's in the air would get left behind. Is that, if birds can't fly, if the Earth's just going to leave the birds behind, essentially. It is an appeal to beauty. Non-circular orbits aren't as perfect as the perfect circles and spheres. Right, the heavens should still be more perfect. Right, and so here, the argument there is that this would be the first blemish. Right, is that other than ellipses, the heavens are perfect. So why are we putting this pockmark on it? And in the third orbit argument is, well, if the Earth's moving, why don't we see parallax? And so here comes Galileo. Galileo is going to do several different things that shatter these objections, that make the Kepler model, the heliocentric model, more palatable to people. Of course, he's also going to pick a bunch of fights. So Galileo first addresses this idea that objects will get left behind if they're in the air, right? And that's coming from Aristotle. Thinks that objects are going to go to the Earth and come to rest. They run out of energy. And Galileo, through a series of basically measurements, basically doing the measurements that Aristotle didn't, figured out that the reason that objects lose energy is friction. And that essentially, if you minimize the friction, objects stay in motion until you apply some force to slow them down. And the force that usually slows them down is friction. And so if an object is on a moving Earth and then jumps in the air, it keeps moving with the Earth's speed. And so from the perspective of someone on the ground, objects don't get left behind if they're in the air. So second, he looked at other objects in space. And up until Kepler, the only way to do that is to stand outside and look up, or to make naked eye observations. But the telescope was, now Galileo didn't invent the telescope, but he did take it and use it for observation. He made it a research tool. And he looked at the moon and he saw that the moon was not a perfect sphere. It had craters on it. It was not an ideal object. He looked at the sun and he saw sunspots. Don't look at the sun with a telescope. He looked at the sun and he saw imperfections. He saw sunspots. That might have contributed to why he was blind as an old man. So he also looked at other objects in the sky, and he looked. Tycho had his measurements, and he thought he knew the distances and the sizes, but he showed that those. Galileo showed that those measurements must be wrong, because he looked at objects that should have been one object, and he discovered individual stars. And the fact that they were blurring together meant that they were very, very, very far away. And if they're very far away, then it's okay that you don't measure parallax. It's just something you can't measure at this time. Right? So that kind of overcomes those objections, but he keeps going. He looks at Jupiter, and he realizes that there are objects orbiting Jupiter. He finds the Galilean moons, and he plots them out. And the idea that an object is not orbiting the Earth, and it's verifiable that it's not orbiting the Earth, means that there's no need to keep this idea of perfection of everything orbiting the Earth. He looked at the phases in Venus, and if you look at the phases of Venus, you should never see fat, bright phases. Never see gibbous phases. You should always see crescents or new Venuses. But Galileo noted, hey, you see these, it only makes sense if Venus is behind the sun in a sense. And so he noted that Venus had to be orbiting the sun. And so you can follow these links if you're following along and kind of observe this stuff. So the other thing he went and tried to do is publicize this. And so there's kind of, this problem of there's ongoing, most of these people are being funded by the governments. Is that they're going and appealing to the kings and the nobility for their money to do this, do their, that's what Tycho is doing, is begging kings for money. But there's another organization, the Catholic Church, who prefers the Ptolemaic model. And, it's not that, it's not the idea of a flat earth or anything like that. It's just that they like the idea, they've been teaching of the idea of the perfect heavens, and so they intervene, and first they're like, well, how about you just make mathematical arguments? You don't have to say it is like this, just say it's modeled like this, is that this model works better, and don't comment on what it actually appears like. Galileo's like, all right, I'll publish a new book about that. And some of the, like Copernicus and, they're not making a "this is how it is" statement. They're saying this is a mathematical model that fits the observation statement. So Galileo is doing more of "this is how it is," and it doesn't help that Galileo's writing in Italian, which makes his ideas more readable. So he makes a hypothesis and publishes this argument, which basically makes the Pope look like an idiot. He has two characters arguing in his book. One of them is called Simplicico, which is, in Italian, you'd probably translate it as stupid or something like that, and simple. And he puts the Pope's words in that character's mouth. And that doesn't work. And so the church is like, "Now you're just picking a fight. No, don't do that." And they put him under house arrest because he's an old blind man at the time. And eventually the church is like, well, everyone else buys into the heliocentric model. We'll go with it again. But they finally apologize posthumously to Galileo in 1992. So they kind of hold some grudges, or it just isn't a big deal at the time. Everyone's dead involved. Yeah. So this is. The church is kind of lagging behind the Renaissance. Is it? There's other times when they'll be ahead. We'll talk about that when we get to the description of the Big Bang versus the static universe that we talked about in Chapter 1. There's more going on here. This is a complicated thing. Some of it's about basically who's teaching and who's funding research, and a lot of this politics is on top of church matters. So, anyway, the big sort of thing that we want to end on here is that, and I notice this when I'm seeing people doing their assignments, the Past Astronomer Project or the Pseudoscience Project, at least a few people picked the geocentric model as an idea of pseudoscience. And I kind of want to spend a little time here. This video is going fairly long. I'm sorry about that. I want to talk about the science. Like, y'all learn in elementary school, and you've probably seen some of this, the idea of the idealized scientific method. And I hope in my tone of voice you saw the scare quotes I held up in my fingers. The idealized scientific method. The idea is that you ask a question, you suggest a hypothesis, you test the hypothesis, and it either supports or does not support, right? This is the statistical scientific method. You do hypothesis building. Now, that is how science can work, but there is deeper levels, right? And one of the things that you try to learn here in your stats class is the idea that there's uncertainty. There's how much can we trust our data here? But another thing is that this idea of make a prediction, run an experiment doesn't work in astronomy. And astronomy is clearly a science, but it's an observational science. Is you make a model, you make a hypothesis, and then you test it against data you have. You don't come up with a new experiment necessarily. I mean, there are coming up with new techniques, but you're still observing and taking the data as it comes in. You're not creating data, right? So this idea sometimes we just look at stuff. Sometimes it's not a hey, here's a specific hypothesis that we can test. Sometimes it's just, well, the planets go backwards. We need to explain that somehow, And so the problem with the geocentric model is that it was wrong. Not that it wasn't achieved scientifically. There was taking of data, and it was the best data that they had available, and building a model based on it. And that is completely scientific. It failed ultimately, but it took thousands of years for the ability to prove it wrong and to come up with a better model. Now some of the features of geocentrism absolutely were pseudoscience. The appeal to beauty, the idea of perfect circles and perfect spheres. There was no way to test that, and there was no, it didn't lead to any improvement in the model. It was more of aesthetics. And so, that, in a sense, wasn't a testable thing. That was more pseudoscience. But this is kind of the thing, is what is a modern science got that other forms of understanding the world doesn't? Modern science, it starts with the Greeks' idea of only having natural causes. Right? If you see something, it has to be explainable, and it can't use supernatural intervention. Then, once you're starting to build a model, you take the simplest model that you can, Occam's razor. Right? The simplest, the most economical explanation is the best. Right? And so that's where the Greeks kind of went wrong, is the simplest model would put, well, there was some debate. They thought the simplest model would put the Earth at the center of a small universe. But it's not unbelievable that the simplest model might put the stars very, very far away, and that's why you can't see the parallax. And the simplest model for the planets going backwards is the Earth passing. Right? So that's kind of a little debatable, but the idea is they certainly made complications to the geocentric model that weren't needed in the heliocentric model. The third key thing is there has to be testable predictions. So if you want to boil that down to 6 words, natural causes, simple models, testable predictions. And if it doesn't fit, you have to quit. You have to come up with a better model that does fit. So, I'm sure Mr. Brown talks about scientific theories if you've taken chemistry. And, because he's told me that, we kind of discuss this every once in a while. What is, right? People use theory as basically a scientific guess. And that's not how we treat it. A theory is almost as a proven thing in actual science. Idea is a theory is something that has not failed a crucial test of validity and has a lot of evidence for it. And it explains a lot of stuff simply. Right? So a hypothesis is a thing that is the wild ass guess. But a theory is something that's a bit more solid. So I mentioned astronomy. Here is a horoscope that was done up. Note the name Johannem Keplerum, which is Johannes Kepler. Kepler did astrology, and the reason he did it was to make money. Right? Is that there was a need for prediction. Right? Is that governments, kings wanted to predict the tides of battle or whether their undertakings would go well. And it was thought that you could look at the sky and that there were hidden influences on humanity based on where the stars were in the sky. And so people hired astrologers to do that. And this, things have been going along thousands of years in various forms. And it's all about, the astronomers either believed it or they needed to make money, and so they did it. Right? So, basically, if you look at astrology now, the way people look at it now is kind of, there's just what day are you born on, what category do you fall in, and the descriptions of people's horoscopes are basically junk. They're basically no substance to them. So there's very few testable hypotheses, and most tests go on is that these things aren't any better than flipping coins. They're chance. So astrology isn't a science. It's an activity. It's an entertainment. There's some other things. There's bits of pseudoscience all around. But I did want to talk about calendars and the Mayans. All right. The way their calendar worked is they had cycles of certain lengths that they assigned unique times for, and these cycles let them schedule their various events. Right, and these cycles were different amounts. Some of them were based on years. Some of them we're not sure what they were based on, but they repeated, and then some of the cycles repeated over and over. And so there was, in this Dresden Codex, the end of the Codex is showing the end of the calendar, and then there's this deluge in the last image. Kind of, you can see that there's a serpent, and it's doing something, but just didn't look good, right? And this is the kind of idea is that their calendar had a bunch of epochs in it. And they told the story of after each epoch, there was something going on, wind or fire or rain or jaguars. And so they're counting time through these cycles. And eventually the calendar ends again. And they're not telling us anything about what's going on. So the start of their last cycle was in 3114. You add the length of the cycle to it, and that cycle ended the 21st of December 2012. And so people took that to be, hey, the world is going to end because their calendar ended. Well, calendar ends every 31st of December, and we just go buy another one, right? So there's some questions here. Did they understand the whole of the universe and of planets and the Earth? Well, we don't understand it. No one understands it clearly. They had some understanding, but not enough to predict the end of the universe. Were their predictions unambiguous? It's hard to tell if they even predicted anything. You know, the stories that are told here could very easily be, mythological, not predictive. Um, Essentially, what we're talking about is people have just made up a story based on an incomplete record of other people's stories. And so, this whole 2012 thing was bogus. So that's it. That's the bit. I wanted to talk a little about pseudoscience and a little bit about wrong science, actual science, but comes up with the wrong predictions. So that's chapter 3. I'll upload this. Y'all should be able to get to it. I hope this is interesting and worthwhile. So I'll do another video that has calculations. That may come Friday, but I'm going to try to squeeze it in today. It's getting a little late. But I just want to run a quick calculation. And in chapter 4, will probably be calculation heavy, so we'll do a lot more of that. But chapter 4 will be physics, 5 will be light, 6 will be telescopes, and then we get to the planets. So, I hope you enjoy this. This is where I stop.